from the City College of New York. My name is Saborna Berry, and welcome to lecture number 5 of ordinary differential equations. Today, we're doing non-homogeneous second-order linear differential equations. A mouthful, right? Well, you'll remember that last time we did homogeneous second-order linear differential equations. What does that mean? Well, it's just equations of the form y prime prime plus ay prime, where a is a coefficient, by, where b is a coefficient, so these both are constants, is equal to 0. Pretty simple. And just to review, how do we actually get through these? Well, all we have to do is use the quadratic formula. So, let's try an example. Y double prime plus 3y single prime plus 4y is equal to 0. So what do we do here? Well, our solutions are just of the form e to the rt, where r is our two solutions to this equation. So in this case, we have minus 3 plus minus the square root of 9 minus 16 over 2 times the first coefficient. We can always divide through so that the first coefficient is 1. So we're just dividing by 2. So all we get is minus 3 plus minus I root 7 divided by 2. Or in other words, minus 3 halves plus minus root 7 over 2i. What the heck was that noise? So now all we have to do is plug it in right over here to get e to the minus 3 over 2t times e to the plus minus root 7 over 2ti, or 7 over 2it, you could put. So now we use Euler's formula to expand this, and we get cosine rad 7 over 2t C1 cosine rad 7 over 2t plus C2 sine rad 7 over 2t. And you might say, well, since you're doing a plus minus, shouldn't this be negative? Well, the thing is, since we're using coefficients, which are constant, we can just adjust those values in order to compensate for that. So, yep. So that's where we get everything over here. So our general solution is just e to the minus 3 over 2t times c1 cosine rad 7 over 2t plus c2 sine rad 7 over 2t. No, not rad 2 over 7. Okay, yep. Doesn't look too clean, but this is our general solution to a homogeneous equation. Alright, so today there are actually 2 methods of solving these equations: variation of parameters and undetermined coefficients. Now we're actually going to be covering variation of parameters next time, as it's a little bit more complicated, but it's also much more general. This thing only works for polynomials, so things of the form a0 plus a1 x plus a2 x squared plus an x to the n. It also works for exponentials, and it works for trigonometric functions. And you might say, well, isn't that basically all we need? No, actually. Here are some examples for which it doesn't work. For example, 1 over x and logarithms as another example, or even inverse trigonometric functions. Tan is not an inverse trig function, but it is a regular trig function multiplied by an inverse. So I'm considering it 1. So that is why undetermined coefficients is not really the more widely used method, but these ones come up a lot more than these ones. So this is a lot simpler, which is why we're going over it today. So why are these the most popular? Well, take, for example, a polynomial function. F of x equals a0 plus a1x plus a2x squared plus dot 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 an x to the n. Now, what's the derivative of this? Pretty simple, right? F prime of x is equal to a1 plus a2 x1 plus a3 x2 plus dot 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 an x to the n minus 1. What's f double prime? It's just a2 plus a3 x1. Oh, and yes, once you do the whole power rule thing, the powers come off and go into the coefficient. But these are constants anyway, so I'll leave them as they are right now. But if you're really a nitpicker, we could just put these. Okay, so then we have 2a2 plus, once you take the derivative here, it's 6a3. Once you take the derivative for 4 and then do it again, you get 12a4, and so on and so forth. N minus 1 times n, or rather n squared minus n, an xn minus 2. And this keeps going on and on and on until at some point, once you've taken n derivatives, well, let's think about it. When we took 0 derivatives, a0 was the constant term. When we took 1 derivative, a1 was our constant term. When we took 2 derivatives, a2 was our constant term. So when we take n derivatives, of course, an is going to be our constant term. And then what happens once we take the derivative of a constant? We get 0. And then 0 again once we take another derivative. And 0 again once we take another derivative. At some point, we can stop caring about these derivatives altogether because they're the same. After a finite amount of derivatives, it eventually becomes the same after you differentiate it. E to the x follows the same rule because e to the x is, of course, once you differentiate it, you get the same thing again and again and again. Now, this rule also holds up with constants because when we talk about undetermined coefficients, we can just play around with the actual coefficients because we're just solving a system of equations. So if we have e to the cx, and then we have f prime of x equals c e to the cx, f double prime of x equals c squared e to the cx, the main term, the main thing to care about is always the same. It's just the constants that change in every single iteration. However, this does not hold true when you're doing e to the x times some function, because after one derivative, then you have z prime of x, e to the x, z of x. And then once you take the derivative again, you are then met with something nasty, a product rule. G prime prime of x, e to the x dx, plus g prime of x squared, e to the x dx. And if you keep doing this, the product will spiral more out of control, turning it from 1 term to 2 to 4 to 8, and so on, and it just spirals into chaos. So we don't like this. And so, let me pick up this marker cap that I dropped right over here. That's our limits for e. And now let's talk about the trig functions, because you probably know that after 3 derivatives, they get mapped to themselves. So you get f of x is cosine x, f prime of x is minus sine x, f double prime of x is negative cosine x, f triple prime of x is sine x, and f quadruple prime of x is cosine. And in the same way, if f of x starts out being sine x, well, you can see the pattern go on over here. We loop back around to there, and then it takes 4 steps again for us to get back to sine. And if we put any coefficient in here, it still holds true, but not if we put a whole function, sine f of x, in there. So, all right, that's our limits. But how do we actually use this thing? Haven't even gotten to that yet. So let's erase this example, and let's come up with something like f double prime of x minus 2 f, well, no, this isn't as creative, minus 5 f prime of x minus 6 f of x is equal to, let's think of something, 5x cubed. All right, how do we solve this? Well, here's the thing. And you know what? Let's just add an x squared for extra spiciness. So here's the thing. Let's look at the derivatives of this function right over here, g of x. G of x is 5x cubed plus 6x squared. G prime of x is 15x squared
12x.
plus 12x. G double prime
30x 12.
comes 30x plus 12, and g triple prime
30.
comes 30, and g quadruple prime is
0.
everything. So it is reasonable to assume that f of x is to the 3rd degree, because it has to turn out being a polynomial at the end, so it has to be sum of polynomials at the beginning. And when you really think about it, this is a 3rd degree polynomial. The degrees only decrease as you take more and more derivatives. So this one has to be a 3rd degree polynomial, not this one. That doesn't work out. So, of course, it can't be exactly 5x cubed plus 6x squared. If we try plugging that in, it's not going to solve the equation. We get 30x plus 12 minus 75x squared minus 60x minus 6 times the original function, which is minus 30x cubed minus 36x squared. Already, we can see that the only cubic term is way larger than we would have liked it to be. So we can't go with that. So here's what we do. We take the particular solution, yp is, or if you want to be consistent with notation, fp of x is equivalent to ax cubed plus bx squared plus cx plus d. Then when you take fp prime, you get 3ax squared plus 2bx plus c. When you take fp double prime, we get 6ax plus 2b. Now, let's sum those up, because we only go up to double prime because those are the only derivatives in this equation, but no matter how many orders this equation has, this will work out for you, as long as you have the right thing on the other side. So, you have that the sum of these in our differential equation, what you have to do is multiply these by the coefficients we find, because it's not like our equation is just f double prime of x plus f single prime of x plus f of x is equal to our solution, is equal to the function on the other side. We have these actual coefficients, so we need to multiply by them before adding to the final result. No, sorry. So minus 6 f of x minus 5 fp prime and f double prime. Pretty simple. And all this has to do is add to what's on the other side, just like these. Pretty simple, right? You can see the correspondence. So we get ax cubed plus 3a plus b x squared plus 6a plus 2b plus c x plus 2b plus c plus d as our constant. Now 2b plus c plus d has to be equal to 0 because we have no constant term. 6a plus 2b plus c also has to be equal to 0 because we have no first degree term. 3a plus b needs to be equal to 6, and a needs to be equal to 5. So with the knowledge a is equal to 5, 3a plus b is equal to 6 is easily solvable because 3a is just 15, so that means b is -9. But wait, we made a critical mistake. And what is that? Did you catch it? We forgot to multiply through. So we actually should be getting negative 15ax minus 10bx minus 5c. You see how drastic that is? But we also have to multiply here, get minus 6ax cubed minus 6bx squared minus 6cx minus 6d. Crazy, right? So we get that 2b minus 5c minus 6d is equal to 0. We get that, let's look at all the first degree terms. You get 6a minus 10b minus 6c is equal to 0 again because there are no first degree terms. We get all the second degree terms together, minus 15a minus 6b is equal to 6. And finally, 5a, or rather, minus 6a is equal to 5. So you get a is equal to minus 5, 6 over here. Then what happens when we multiply into here? We got minus 5 over 6 times minus 15, which cancels out right this way. So we get 5 over here, and then these cancel out as well. So we just get 12.5. or 25 over 2. And then all we have to do is subtract that from 6b. We get 6, also known as 12 over 2. So then we get minus 6b is equal to negative 13 over 2. Or in other words, 6b is equal to 13 over 12. Wow, there's a frog on my tongue today. Tongue, not tongue. Then once we get c, we get 6a, and a is minus 5 over 6, so this is perfect opportunity. Minus 10b, this is not as perfect of an opportunity, but we can just convert minus 5 very easily. And then we have minus 6c is equal to 0, so that means that 6c must be equal to minus 170 divided by 12. Oh, no, sorry, minus 190 divided by 12, which if you put in the effort to actually cancel that out, this gives you, sorry, I've been doing a little bit too much math, minus 95 over 6, so C is minus 95 over 36. And finally, figuring out D can't be the hardest thing in the world. We just get 2b, which is 13 over 6, minus 5c, which is plus 95 times 5 over 36. This shouldn't be the hardest thing in the world to figure out because, of course, it's just 475. And then we get minus 6d is equal to 0. So we put the 6d onto the other side. And so, once we actually get this whole mess together, $553 over 36. And you can verify for yourself that these work, but our actual solution is yp of x is equal to negative 5 over 6x cubed plus 13 over 12x squared minus 95 over 36 x plus 553 over 36. Now that I think about it, it was a bad decision to do this as a cubic. Well, that's it. We've run out of time, so thank you everybody for watching, and we'll see you in the next one.